My name is Will Figueira. I'm a research academic at the University of Sydney in the School of Biological Sciences. Today I'll be presenting some work looking at the patterns and processes driving range expansions of marine organisms, specifically along the southeast coast of Australia, mainly making a specific focus on the processes, how variable they are, and how we're learning to understand that variability so that we can ultimately predict the speed and extent of different range expansions along the coast. What I want to talk today about is, I may have overstepped myself on my title. I realized I was putting this talk together. I am covering these sorts of things, but admittedly, because of my research, they'll be focused on certain taxa. And especially, I'm going to focus on process, really. I anticipated that my good friend Alistair would set me up well with some information on range shifts and climate changes, and he did, which is great, so I'll cover those very briefly. But I want to focus, as I said, on the processes, partly to impart an understanding of the complexity in trying to determine what's going to be where, when, right? That's what we want to know. There's significant, if you want to look at it, probably the most apparent scale in marine systems, significant productivity shift issues that Alistair alluded to. Where are the stocks going to be, and how does that affect people? But in order to predict that, there's a lot that goes into it, and we've gone through some iterative steps in our history and how we approach that. And I suppose my research, I think, is trying to take another step, adding yet another level of complexity, but I think hopefully with some useful insights. So I'll start just by hitting the ground running by saying, right, so range shifts are happening, just like Alistair said. There's been several reviews over the last 15 years, more in the last 5 years. This is Elvira's most recent one, Elvira et al., I should say, a massive group of individuals. Just showing global review. This isn't marine, this is global, well, it's terrestrial and marine. That, of 80% of the response variables that they basically trolled up 1,700. They're seeing, and these response variables are changes in distribution, phenology. So that analogy we heard the first day about picking the grapes sooner every year, right? This is related to phenology, right? The ripening of the crops are happening sooner. Changes in abundance, calcification, demography, all these things, 80% of these response variables are consistent with climate change. And interestingly, and very related to what I'm talking about, is that the rates of expansion, if you just say how fast are these ranges expanding, how far the front's expanding per time, they tend to be about 10 times faster in marine systems than in terrestrial systems. In Southeast Australia, again, highlighted much better by Alistair than this, we're seeing, this is just highlighting a couple studies. First from Elvira's study, about 80 species that they looked at, they had data for. 45% of them had changes consistent with climate change. Looking more specifically with the fish from Peter last study, again, this was one highlighted by Alistair. You're seeing, looked at 300 species, 56 had changed, and 45 of those were consistent with climate change. So it is happening, in addition to all those other examples that Alistair gave. And why is it happening? What's going on in marine systems? So this is the short list of things that climate is affecting marine systems. We just heard about sea level rise, right? Uncertainty in freshwater flows, more rainfall, less rainfall. This obviously affects freshwater species as well as estuarine species. We all know about decreased pH, ocean acidification, this potential for increased storm activity, the physical damage it can do, and of course, increased ocean temperature, right? And I'm going to focus today mainly on increased ocean temperature, and we're having a PC Mac issue. That was supposed to just this one is supposed to go red in a really cool way and stand out, increasing ocean temperature. But now everything has it. I'm not focusing on everything. I'm focusing on increased ocean temperature, partly because that is one of the main factors that affects everything about ectotherms, and the vast majority of marine organisms are ectotherms. Whatever's happening with the water temperature, that's what's happening to their internal bodies, right? So that's why I'm focusing on it today, and that's where most of my research has been. So again, we have evidence that the air is warming globally. It's warming in Australia as well. But of course, relevant to my discussion here, the oceans are also warming again, as you've heard. Especially Southeast Australia is warming at a rate faster than the rest of the planet, such that we're winding up with these hot spots along the coast. I'll show you some data later from some of the same data sets that Alistair has shown that really demonstrates that slope of warmth increases as you go further down the coast. Right, so what do we need to have a range shift? This is sort of how I break it down in my head. First, you got to have some way to get outside the present range. Secondly, you need to survive wherever you wind up. And then eventually, for it to be a proper range shift, you obviously need to be reproducing. So I want to talk a little bit about that first, migration outside the present range. So marine animals, vast majority of them, and certainly the case for most fish species, have a bipartite life history where they've got pelagic phase, the larvae are spawned, or they're hatched in eggs and they hatch out. Either way, and that stage can last from days to months. They drift around, right? Sometimes they swim, sometimes they don't. I'm not getting into a lot of that. But the point is, then they settle at some point or they morph into adult forms. And this stage gives them a potential for movement across great distances. It also makes population biology, which is overall, I suppose, what my discipline is, really what I do, difficult. What is a range? How do you define a range? You have viable core populations. You have external areas that export to non-viable populations. And at the very extreme, you might have areas where there's sporadic settlement only. And the context of a rapidly changing climate, right? These are obviously dictated in many ways by the environmental conditions. And when those environmental conditions are rapidly changing, what's going on in this space can be quite dynamic. And I think can happen quite quickly because you have the option, even very, very far south, and I'll work off some of my own work here, to have individuals suddenly around because they can make it so far out. So it's not this case that every year they're moving a kilometer, right? It's every year, as I'll show you, some of these animals are moving thousands of kilometers, and it becomes more an issue of are they surviving? And how do they move? Well, ocean currents, right? They can swim, they do swim. The more we know about larval fish, the more we know what incredible swimmers they are. But even invertebrates can vertically migrate in different water columns and selectively move with tides, things like that. But you've also certainly, one of my examples is going to focus here, obviously, but you've got these boundary currents that flow from the equators to the poles, and they're often very strong. And wherever you have these, you have a potential, especially for very high advection, in the case of what I'm talking about, to get these little exotic visitors from the tropics, or the colorful wave of terror from the north, we often call it down here. And this is one of the nice things about climate change, right? You stick your water in Sydney Harbor and you see all these cool little things, right? So these are all fish that we see in Sydney Harbor. And that, I just wanted to yell it out. Ketodon auriga, I wanted to yell it out. That's the threadfin, and it is one of the most common ones we see down the coast. So we've done a lot of work. I've been working on this for sort of 9 years now since I came to Australia, and a little bit before I left because I lived in North Carolina. And we have tropical fish there as well. But we've looked at their density across gradients, through New South Wales, and you see what you kind of expect with some ups and downs. There's more to the north than there are to the south, so they're being supplied from the north. Same thing with richness, tend to get a few more species to the north than the south. And this is from early work. We've done a lot more since then. But you also see these periodic cycling up and down. So they're arriving, they're dying, they're arriving, they're dying every year. They arrive in the summer. They don't usually survive the winter. I'll get back to that. So how do they get there? Well, some of our work has, looked more specifically. You wouldn't think it's any genius to pick up that it's probably the EAC involved, and that's what our research has demonstrated. It's a very dynamic current. So it's not only the biology, but also the oceanography that's affecting the timing, impulses, and strength that you see these guys arriving. So I would say that we've got mechanisms, certainly in marine systems, for these animals to get here, especially using this tropical temperate connectivity, tropical vagrant things as an example. One big caveat that I'll throw in there is that we do know there is serious potential for warming oceans to affect connectivity patterns. Animals grow more quickly. They potentially, where their larval periods are constrained by getting to a certain size, that larval period may become shorter. But at the same time, we have OA going on that, at least for invertebrates, in some cases and not in others, affects their development. And in fish, it can affect their sensory ability. So without going into detail, there's plenty of scope for this phase, this part, to be affected by ocean warming. But nonetheless, there's a mechanism. So they are getting here. What about survival and growth? So this just highlights some data from, I think it's Shelly Beach probably, where you see tropical fish increasing 1 year, falling off, coincident with temperature, and another year where the same thing happens. And I can show you a million of these graphs for individual species, and you get the point. Temperature seems like it's involved. And this is some satellite SST data, sea surface temperature data, for a bunch of sites along the coast, one tree being quite warm, Marimbula, this is Bateman's Bay, Jervis Bay, Sydney, Port Stephens, Lord Howe Island, Coffs Harbour, Byron Bay. But you see these bumping around, and I'll note a couple of years here. There we go. 2001 and 2006 were quite warmer. Sorry, these are average winter temperatures, by the way. I should have pointed that out. Average winter temperatures. And 2001 and 2006, we had quite warm winters. And that prompted a little bit investigation into, okay, if overwinter survival is a bottleneck, then maybe we'll see more after winters like that. And what you find, if you look at average winter temperatures on this axis, and doing some fancy mumbo-jumbo stuff, because we're quite clever, about the probability of surviving that winter. So this is based on field observations at a whole mess of sites for all these species. What you find is these really strong sigmoidal relationships, threshold curves. At a certain temperature, boom, they seem to survive. So that's interesting, and it lends evidence that there is a strong relationship with temperature, as you expect. But an interesting thing falls out of that, and that in most of these, the thresholds were about 17, 18. But I know for many of these species that their critical thermal minima, that is where they can no longer function and they flop on their sides, is much lower. So they can survive. Why aren't they? And again, obvious answer for the ecologist is, well, things are eating them, things are picking on them, and they're dying before they would have normally. So what it highlights is, in order to really understand when something's going to survive as temperature changes, we need to really think about the ecology. So we've done a little bit of work on that, but it involves understanding that, things, performances always change with temperature. They all usually have an optimum, and this performance goes from cellular level all the way up to things like growth and reproduction, right? And when they're below their optima and the temperature increases, that performance increases and vice versa, right? So that's the logic. That's what we call a reaction norm. That's just a little background. So one of the interesting questions is then, so what's happening with these little fish when they come down into this novel environment relative to the fish that are already here? So if we look at if we look at some temperate fishes, this is the graph for a little temperate downside fish up here, this guy, versus one of the tropicals. This is just abundance over time to point out to you that the temperates are here year-round. Tropicals die out in the winter. So it'd be interesting to know what's going on. How are they both each affected by temperature as a start? So we did a few things. We looked at their growth rates. At a couple temperatures, the temperate fish, no real difference because we're kind of straddling its thermal optima. The average temperature in Sydney is kind of 20-ish. Whereas for the tropical fish, you see a massive increase in growth when you give them when they're in warm water. And interestingly, same thing for burst swim speed. No real difference, no significant difference anyway for the temperate fish, but for the tropical, they swim much faster when you put them in warmer water. So now we're starting to relate temperature to these ecological relevant things, growth and certainly speed and getting away from predators. So then we said, all right, well, if getting away from predators is the issue, you should see more mortality for a tropical fish, and that mortality should decrease as you increase the temperature, if you're in it with a temperate predator. So we firstly just took a tropical prey, a temperate prey, and a temperate predator. And we looked at their speeds. And exactly as you expect, over 3 temperatures, 17, 21, 25, tropical prey gets faster, temperate prey gets slower, temperate predator gets slower. So when you do mortality trials, we actually put them all in together, look at mortality over time, plot that up. Temperate guys, first of all, didn't survive well enough at 25 to do a trial. That's why there's nothing there. But the point is, because they're both getting slower at about the same rate, there doesn't seem to be really any net change in the mortality outcome of that interaction. They're both slower. They still catch about the same amount. Mortality is still the same. For the tropical fish, though, as temperature increases, it's getting much faster. The predator is getting much slower, and you see a massive drop in mortality. So this lets us link basically the performance ratio, if you will, just divide literally the speed of the predator by the speed of the prey. And that's a performance ratio to mortality. So imagine the faster the predator is, we're out at this end of the curve, the higher the mortality. So this is data from this trial. So whether this is linear, I've plotted up a line. I don't even know if it's significant. That's not really the point. The point is there's some positive relationship between the two. And in my mind, this lets me build a bit broader theory of how temperature ultimately will affect mortality in these outcomes when you've got novel species invading new habitats. If you just look at, if this is my tropical prey reaction norm, and they're a bit more warm adapted, and this is my temperate predator, and of course it's a bit more cold adapted, and you look at that performance ratio, the same one here, just plot it up, just divide this by this, and you see what happens is that the performance ratio drops off quite dramatically as it gets warmer. That is, the speed of the prey is getting more closer or higher than the speed of the predator. And then, essentially, you can just do the math and put these two together and look at the effect of temperature ultimately on survival, because you've got this link through the performance ratio. And what you see is this, and this isn't any really fancy math. This just pops right out of it. It shows you, as temperature increases, the survival rate has a threshold, and wham, bam, you're right back to exactly what we saw with the field data. So I think what this is telling us is it gives us a really strong way to relate. It's sort of not rocket science. You've just got species with different thermal optimas, and as those diverge more farther apart, you get a much even steeper reaction. So things are going to happen quick, right? When it does happen, when they get to that threshold, suddenly they survive, right? And So that's great, but the real problem is, unfortunately, reaction norms aren't stable. They're not always the same, and they can change. You can look at our data, and you can say these are actually coastal, these are data fits for a few of the species. There were separate fits to the data for different sites. These are coastal New South Wales sites, okay, these ones highlighted here for these two species. These are all fits that were for Lord Howe Island, where it's warmer. Ironically, by 2 or 3 degrees on average, annual average temperature is a bit warmer. And you basically see about that much of a difference in that thermal optima, that, as the mathematicians would call the point of inflection, the steepest point of that curve. So it argues that these Lord Howe Island fish are warm adapted in some way. So it's the same species, but we obviously haven't measured their reaction norm here, but they clearly would have different reaction norms, non-overlapping. They'd be separated. So something's happened. So this is cool and annoying, right? It's annoying because we can't just measure the reaction norm for a species and go, gravy, now we can figure out what's going to happen. The reality is they can change, and we all know this because this is what we mean when we say, can things acclimate? Can animals adapt? This is exactly what we're talking about. They're shifting their reaction norms, and I've got there's 2 ways they can do it. I don't want to belabor this. My point of this slide and the next one is to show you it's a variable, so don't get caught up in the details. But they can acclimate, which means within a generation. Us ecologists call that like a plastic response. That means there's no reproduction, there's no natural selection going involved. Just hardwired in them is the flexibility to change their reaction norm in some way, versus adaptation, where there is some genetic process and selection for animals with different thermal optima. These can both be happening in concert, but they can both be happening. So an acclimation response is something like, say you measure at a couple different temperatures the performance of this individual or this group of individuals, and you think this is the theoretical underlying curve, right? And you measured it, this is what you get. If you then subjected them to 5 or 6 weeks at a colder temperature, you may hypothesize the curve would shift, and when you measured it again, you would get values like that. So this is evidence in our world that there's been a shift, there's been an acclimation response. They've shifted their thermal optimum. So now they do better at colder temperatures than they did before. Conversely, you can also have adaptation leading to all kinds of crazy responses, which I put names on here, and I don't want to go into the details. The point is, you can see, for instance, a good way to think of this is latitudinal gradients. Species found further to the south may have cold adapted thermal acclimation curves. They may be broader. They may be subsets of the other. Again, I'm not going to go into it, but the point is these things change. There's lots of data out there for terrestrial and marine systems that thermal reaction norms change. So we've done a little bit of our own work because we want to know, we've got good tropical temperate connectivity. We know that overwinter survival is a bottleneck in our model system of these little tropical fish, but I think it's very extendable to any fish or marine species going to have the same issue. That these adaptation and or acclimation could change those thermal limits. And so basically we want to know to what degree populations can respond to these abiotic conditions that will then increase their persistence. And this is kind of the end of it. What does this mean for the speed of range shifts, right? How can we use all this information to figure out how fast things will be where? The ultimate question. So how fast in the case of New South Wales, are we going to see these little tropical guys living year-round? I was very proud of myself when I saw that. Right? Thanks for the hushed applause. So we've done a few of these. I'll just highlight a few acclimation experiments. This is things where we just measured a swim speed. This is a measure of swimming speed, sustained swimming speed. And this is exactly that graph I showed you. And in fact, that graph was a setup for this one to highlight that when we measured this fish that was kept at 24 degrees, we tested them at 17 and 24, and we get this curve. We keep another batch of fish at 17, and we measure them, and we get this curve. This is acclimation, right? They're now doing much better at a colder temperature than they did before, the colder ones. They've acclimated. So in this case, over 4 weeks, we saw acclimation of this sort of aerobic swimming speed. Interestingly, this is burst swimming speed, which is anaerobic, which is perhaps more relevant for escaping a predator. In this case, we did not see that sort of acclimation. Again, don't be caught up in the details. I say that, and it's like me splashing up there going, this is how clever I am, don't worry about it. The point is, sometimes you see the acclimation, sometimes you don't. We've also done this, we did this with coral sea fish, and they couldn't even handle the 17-degree acclimation. So these guys are obviously adapted to much warmer waters to the point where it was well outside their thermal reaction norm. We've also looked at performance across latitudes. This is obviously key for us. We think these individuals are coming from maybe up here or maybe here and winding up down here. So we wanted to look in this case at individuals from these two locations. So we grabbed a bunch and we tested them. And we look at, this is one metric, what's called metabolic scope. Think of it as how much you can rev your engine up. It's literally the difference between idle and full throttle, right? And it turns out that for most organisms, there's a reaction norm for that too. They have an optimum where they have the most scope. When you've got scope, when you've got plenty of extra energy, and you can reproduce, you can swim, you can chase, you can do all the things you need to do. When you're near your margins, you've got no extra energy. What we saw was these fish from down south in Coffs Harbour, much reduced scope. This indicates they have much less free energy to play with, which is interesting. We don't know this, I won't speculate on why, there's lots of interesting reasons going into the sort of cellular level chemistry, but the point is they're compromised. They're not doing as well as the One Tree Island fish did. That would obviously indicate, in this case, they might have limited ability to be extending their range much further. Interestingly, we looked at their burst swim speeds, though, and there was no difference in that. So they're kind of all over the place, but significantly, no real difference between the burst swim speeds across latitudes for these guys. So they're equally able to escape predators, which is probably pretty relevant, but their aerobic scope is much lower. So again, don't dwell on those details. The point is, we're looking at the same species in a couple different settings, and we're seeing similar answers for certain things, but not for all the metrics. So it is quite variable, and in the context of at least these tropical fish, we've only looked at a few. So the question of what's going to happen in the future, well, again, this is pulled directly from Alistair's work, just to make the point that, well, as you've all heard, it's going to keep getting warmer by at least a couple degrees, maybe a lot more. So, all right, it's going to get warmer. What's going to happen? That's what we all want to know. So the first pass at this is based, solely on current thermal envelopes. Where do they live now? And we use that as a predictor for where they're going to be. Alistair's done a little bit of this work as well with some of these commercial species that he showed you from the fisheries. In this case, I'm using highly uncommercial species. But this is long-term sea surface temperature data. Again, just to show you the trends. Across latitude, you see what I was telling you earlier. You get more of an increase to the south. But you can use this data combined with my other data on thermal optima, and I said about 17.5 degrees is when they suddenly start to survive. And ask the question, what's the proportion of, what's the frequency with which you get such winters that they could survive? And has that changed through time? So that's all this graph does, and it shows you at One Tree, Byron Bay, this proportion of winters that are greater than the threshold. It never changed because they're always greater than the threshold. Down at the bottom, Bateman's Bay, Marimbula, they're always under the threshold. And coincidentally enough, we almost never see any adults overwinter survivors at those latitudes. But in the middle, obviously, interesting things are happening. Port Stevens has marched from no winters to 100% above this since the 20s. Sydney is sort of 4 to 5 winters out of 10 right now. This is published a few years ago. At the time, we were bold enough to say, do the dangerous extrapolation thing. Say, if you fit a line through there, where would it hit 100? And it's about 2080, which conveniently is after I would be dead, barring some miracle, but I don't see it happening. So no one can call me on that, which is nice. But I did have a quick look at our Sydney temperature logger data, and we basically had 4 of our warmest years in the last 10 have been the last 4 years, 4 of the warmest winters. And this is just long reef data, so no crazy magic going with global data sets and satellite observations, just a logger in the water at long reef. So it's happening. So the question is, we can use stuff from the thermal environment, and we can see that it's becoming more favorable, and that's good. So that's a first pass at helping us understand when things are going to be where, if we know their thermal environment, and our first pass is to base their preference on where they currently are. So those are these bioenvelope models, and that's what we do. But I guess what I'm showing, and once again, I have no idea why that's in red. That wasn't really a point that I was trying to make, necessarily bigger than any of the others, but that there are these threshold curves for survival with temperature. So right away, that tells me that things may happen not necessarily more quickly, but maybe more suddenly. And so over the long span, that would probably translate to more quickly. And then you have to include acclimation and adaptation by the individuals within this whole context, right? So you need to be thinking about the ecology and how they're going to interact in the system they're in with the local established competitors and predators, and they're interacting in thermal reaction arms. But also, how are those going to change? Who's got more adaptive thermal reaction arms? And I think in general, this overall will lead us to more rapid changes than we would have expected to see just by bioenvelope modeling alone. And it could potentially explain, associated with this transport mechanism we have in marine systems, why we see such rapid, 10 times faster range expansions in marine systems. I'm not the first one to think that. That was the first theory anybody had about this. But I think this may provide a bit more of the behavioral, physiological, ecological background for that theory, and helps us understand, again, ultimate question, when's this going to happen? And then, just how hard it is to explain to your child when you watch this movie that you're the bastard that took him off the reef into your office. It just occurred to me the other day. I'm that guy, the scuba diver who grabbed Nemo and took him somewhere. Didn't end as well for Nemo with me, but yeah. So that's the ultimate question: what's going to happen? And yeah, hopefully this sort of work can help us understand that a little bit better. And in fact, it's nice. As soon as I saw Alistair, the first thing he charged up to me and said, "That work you're doing, what have you got more species? You got some answers, Because Maria does a lot of the OW work, and we see variable responses for some species this, for some species that. It drives Alistair crazy. We need answers here, right? And so one of our programs is to collect a lot more of this data and hopefully provide some generalities for this types of fish and this types of fish and their interaction. Thanks. Sorry for going a little longer. My name is Will Figueira. I'm a research academic at the University of Sydney in the School of Biological Sciences. Today I'll be presenting some work looking at the patterns and processes driving range expansions. That my good friend Alistair would set me up well with some information on range shifts and climate changes, and he did, which is great, so I'll cover those very briefly. But I want to focus, as I said, on the processes, partly to impart an understanding of the complexity in trying to determine what's going to be where, when, right? That's what we want to know. There's significant, if you want to look at it, probably the most apparent scale in marine systems, significant productivity shift issues that Alistair alluded to. Where are the stocks going to be, and how does that affect people? Of 80% of the response variables that they basically trolled up 1,700. They're seeing, and these response variables are changes in distribution, phenology. So that analogy we heard the first day about picking the grapes sooner every year, right? This is related to phenology, right? The ripening of the crops are happening sooner. Changes in abundance, calcification, demography, all these things, 80% of these response variables are consistent with climate change. And interestingly, and very related to what I'm talking about, is that the rates of expansion, if you just say how fast are these ranges expanding, how far. But in order to predict that, there's a lot that goes into it. And we've gone through some iterative steps in our history and how we approach that. And I suppose my research, I think, is trying to take another step, adding yet another level of complexity, but I think hopefully with some useful insights. So I'll start just by hitting the ground running by saying, right, so range shifts are happening, just like Alistair said. There's been several reviews over the last 15 years, more in the last 5 years. This is Elvira's most recent one, Elvira et al., I should say, a massive group of individuals. Just showing global review. This isn't marine, this is global, well, it's terrestrial and marine. Of marine organisms, specifically along the southeast coast of Australia, mainly making a specific focus on the processes, how variable they are, and how we're learning to understand that variability so that we can ultimately predict the speed and extent of different range expansions along the coast. What I want to talk today about is, I may have overstepped myself on my title. I realized I was putting this talk together. I am covering these sorts of things, but admittedly, because of my research, there'll be focus on certain taxa. And especially, I'm going to focus on process, really. I anticipated